Okay, I'm going to begin section 4.3 now. Now, just a heads up, 4.3 has quite a bit of information in it. Actually, a lot of calculus books would have the information that you see in this section kind of split over into two sections. Okay, so we'll likely have multiple videos here for section 4.3. We're going to look at how derivatives affect a graph. Okay, and the first thing that we'll talk about is the increasing and decreasing test. Let's let f be continuous and differentiable on some interval I. If f prime of x is greater than 0 for all x in that interval, f is increasing on that part of the graph. If f prime of x is less than 0 for all x in the interval, f is decreasing on that part of the graph. And then if f prime of x is equal to 0 for all x in that interval, f is constant on that part of the graph. Okay, now in algebra you can talk about increasing and decreasing functions, you can very easily explain this saying that if you scan a graph from left to right, the function is going to be increasing if it's rising and it's going to be decreasing if it's falling. Okay, and you have to scan from left to right. I'm still saying the same thing here. Okay, it's just I'm using slope of a tangent line, and so if the slope of the tangent line is some positive number, you're going to have the function being increasing on that part of the graph. Otherwise, if it's a negative number, the slope, okay, it's going to be decreasing on that part of the graph. If the slope of the tangent line is 0, you're going to be constant. You're neither rising nor falling, right? So you're constant on that part of the graph. Okay, let's take a look at an example. State the open intervals on which f is increasing or decreasing. Here's just some curve that I drew, okay. Where are we increasing? Okay, open intervals means parentheses everywhere. That's how the book is going to want it. So where are we increasing? Well, it looks like if we're between 0 and 2, and we scan from left to right, the curve is rising. Also, if I were to draw a tangent line, the slope of that line would be a positive number. Okay, so I'm going to be increasing on that part of the graph that is from 0 to 2. Where else would I be drawing a tangent line that has a positive slope? Well, if I'm between, let's see, 4 and 6, and I draw a tangent line anywhere between 4 and 6, it's going to have a positive slope. So I'll be increasing on that part of the graph. And then right here, if you're going from 7 to 9 and you draw a tangent line, the slope of that line would also be a positive number. So we're going to be increasing on that part of the graph. Where are we decreasing? We're going to be decreasing everywhere else, right? If the slope of the tangent line is a negative, you're going to be decreasing on that part of the graph. Okay, another way to describe it is, where's the curve falling if you scan the graph from left to right? Well, if I'm between 2 and 4, and I scan from left to right, the curve is falling. Also, if I were to draw a tangent line anywhere from 2 to 4, the slope of that tangent line would be a negative number. So we're going to be decreasing on that part of the graph. Where else would we be drawing a tangent line where the slope is a negative? Right here, if we're between 6 and 7, the slope of the tangent line is going to be a negative. And then also, if I'm between 9 and 11, and I draw a tangent line, the slope is going to be a negative. And then if I'm 11 or bigger, and I draw a tangent line, the slope is a negative. Now, by the way, for this problem, the point 11, negative 1, you'll notice I've got kind of like a squiggle in the graph there. I intend for that to be a horizontal tangent at that point. Okay, so I wouldn't want to say like decreasing on 9 to infinity. That's not true, because at that single point there, the slope of the graph would be 0. So actually at that single point, you're going to be constant. Now I don't have a min or a max. Okay, Fermat's theorem did not say that. Okay, it said that if you have a min or a max, and f prime of c exists, then f prime of c is 0. Okay, but one of the caution statements that I had mentioned after that is if f prime of c is 0, you don't automatically conclude that you have a min or a max, right? Again, 11.1 is not producing a min or a max. Now here's 9.4 is the highest point in the neighborhood. That's not a hill, okay, but still it's a local extrema can occur at a discontinuity. Now they're not asking for local extrema here, but that's something that I could conclude, if a function is increasing and then decreasing, or decreasing and then increasing, right, I'm going to create a hill or a valley. Let's take a look at another example here. Find the open intervals on which the function f of x equal 4x cubed plus 3x squared minus 6x plus 1 is increasing or decreasing. Okay, I'm going to use the increasing and decreasing test, which is, after we see this example, it's also called the first derivative test. Okay, I'll talk about that here in just a moment. Yeah, so in the increasing and decreasing test, I need to know the derivative, right? I need to know where's the derivative positive, where is it negative, where is it equal to 0. So let me calculate the derivative here. F prime of x would be 12x squared plus 6x minus 6. And I want to find my critical numbers. Remember, a critical number is a number that you plug into the derivative and it will return 0, or it's a number that you can't plug into the derivative. All right, so I'll set the derivative equal to 0. Can make the numbers a bit nicer by dividing by 6 on both sides. And 2x squared plus x minus 1 equals 0. That's going to factor nicely as 2x minus 1 times x plus 1. Set the factors equal to 0. You get x equal 1/2 and x equal negative 1. Now these two numbers are my critical numbers. The next thing I'm going to do is I'm going to build a table revolving around the real number line and these two critical numbers. Okay, and so I've done that. Now, in this first column, I'm representing all the numbers that are less than negative 1. So my interval is going to be negative infinity to negative 1. In the middle column, I'm representing all the numbers between negative 1 and 1/2. So that interval would be negative 1 to 1/2. And then in the last column, I'm representing all the numbers bigger than 1/2. Using interval notation, that would be 1/2 to infinity. Here's the table template that I would like you to use for the increasing and decreasing test. Okay, we will be using similar table templates for other tests in this section. Okay, you'll see me doing that in the notes here. So I'm going to say interval, number chosen, value of f prime, and then the conclusion. I've got my 3 groups established, these 3 intervals, and now the next thing I'm going to do is I'm going to choose any number I want, but it's got to be in that interval. And then once I have that test value, I'm going to plug that number into the derivative to see if I get a positive or a negative value. All right, so let me do that. I need to select a number that is in the first group here, any number I want, just as long as it's less than negative 1. Like if x is negative 2, and I plug that into the derivative. Okay, so negative 2 squared is 4, times 12 is 48, minus 12 is 36, minus 6 is 30. Now the conclusion, so all I really care about is if the value of f is positive or negative, right? That's what the increasing and decreasing test is all about here. So if f prime of x is positive, f is increasing on that part of the graph. All right, my conclusion then would be that f is increasing on that part of the graph. And that's what I want to find, right? I want to find the open intervals on which f is increasing or decreasing. Column 1 is done. Okay, so how about column 2? I need to select a number that is between negative 1 and 1/2. 0 would be a good number. If I plug 0 into the derivative, I get negative 6. And the fact that that's a negative, that means that I would be decreasing on that part of the graph. All right, so my conclusion, I'll just write decreasing there for column 2. In column 3, I need to select a number that is bigger than 1/2. So like if x is 1 and you plug that into the derivative, 12 plus 6 is 18, minus 6 is 12. And since that's a positive, I'm back increasing again. Okay, so I'm going to be increasing on the interval negative infinity to negative 1, and then also on the interval 1/2 to infinity. I'll be decreasing on the middle part there, negative 1 to 1/2. Okay, a couple things before we look at the graph of this curve here. Number one, we will be doing quite a bit of things with these test value tables, they call them, okay? Now your book is doing a similar thing. They're making a number line with the critical values, and they're selecting test values, and they're going to see if they're positive or negative to tell where you're increasing or decreasing. We're going to be using these charts for other things also, okay? So I'm going to want to see the chart, in your work, and I'll want to see it filled out and that with these test values. Now, when you select a test value, it can be any number that you want as long as it's in the interval. Now, when you write down your interval, make sure that you're using open intervals everywhere, okay? No brackets. You see, a bracket means that I'm including the number, right? So if I'm including the number, I'm able to select it as a test value, and I don't want to do that because I already know what happens when x is negative 1 or x is 1/2. I get 0 as a return value from the derivative. Okay, so that doesn't tell me if I'm increasing or decreasing, right, since 0 is not a positive or a negative number. All right, use any value that you want, any test value, but don't use the critical numbers, is the point. Okay. Of course, at these two spots, I'll be constant. So if I take a look at a picture, okay, here's the graph of this curve, and I've got some points plotted there. Of course, I could set up a table and plot some points, but I'm going to be increasing on the interval negative infinity to negative 1. So the curve will be rising there as long as I'm less than negative 1. Now there's a pretty steep slope, but if I were to draw a tangent line, it should be slanted in the positive direction. Okay. I'm also increasing on the interval 1/2 to infinity. So the curve is going to be rising on the interval 1/2 to infinity. I'll be decreasing on this middle part, right? So the curve will be falling from negative 1 to 1/2. So if I draw a tangent line anywhere, the slope of the tangent line is going to be a negative. Now, the fact that I'm increasing and then decreasing means that I'll be producing a local max at the point when x is negative 1. When x is negative 1 and you plug that into the function here, you should get 6 in return. Okay, so this point, negative 1, 6, is a local max on the graph. Now, if I'm decreasing and then increasing at x equal 1/2, that'll mean that I'll produce a local min at that spot. When x is 1/2 and you plug that into the function, you should be getting negative 3/4. That's what I was getting. Okay, so this point here, 1/2 negative 3/4, that would be a local min on the graph. So really, just to follow up with the increasing and decreasing test, we can identify local mins and maxes. Well, that's helpful when we sketch a graph, right? Where's the hills and valleys? Okay, that's useful information to me. Now from that, we have the first derivative test. Okay, and it says, let C be a critical number of a continuous function f. If f prime of x changes from negative to positive at C, then f of C is going to produce a local min at that spot. Okay, you're gonna go from decreasing to increasing. There's a valley there, producing a local min. Item 2, if f prime of C changes from positive to negative at C, then f of C is a local max, right? If you go from increasing to decreasing, there's going to be a hill on the graph, creating a max at this spot, whatever C is. Item 3, if f prime of x does not change sign at C, then f of C is neither a local max nor a local min. Okay, so like if I go from decreasing to decreasing, this point here is not a local max or a local min. Okay, now it's a key point on the graph, just like up here. This was a key point on the graph. There's a something interesting with the curve. It is like a little squiggle thing, but it's not producing a min or a max. The point, I guess, is to say that the first derivative test is really just the increasing and decreasing test, but then you're going to state where you have local extrema. Okay, like there's nothing new here, right? From this table, I can know where I've got a local max or a local min. And again, that is useful information when I sketch a graph, where are the hills and valleys. So, okay, we'll stop right there.